Hi everyone, welcome back. Today we're doing day 23, binary search tree level order traversal. This is a continuation of the previous challenge, which was where we got the height of a given root of a binary search tree. We also went through how we could break that problem down to the solution of two subproblems. And in this case, the solution to the height of a binary search tree is the max of the height of the left and right child plus 1. But there was one additional detail which I didn't mention, was that the previous implementation that we had was really a depth first search traversal of the binary search tree. Calling get height on tree would call get height on 2, and get height on 2 would call get height on 1. And once the result is returned back from 1, 2 would check the right side, there is nothing, and 2 would return the height to 3. 3 would then proceed to get height of its right child, and similarly in this fashion, 5 will call get height on 4, 4 will return the result back to 5, and 5 will call get height on 7, 7 return result back to 5, 5 return back result back to 3, and we return with the height of this binary search tree. So notice that as we trace the traversal, we are really traversing in a depth-like fashion where we are going down to the children before we proceed to check the other children of a given node. And this is really the opposite of what we have to do over here. In this case, for this task, we will have to perform a level order traversal, also known as a breadth first search. And what this means is we will have to visit each level of a tree's node from left to right, top to bottom. We're given a pointer root pointing to the root of the binary search tree, and we have to complete the level order function as shown on line 20 and line 21. And in this case, HackerRank is really nice to say a queue will probably be helpful if you want to implement a level order traversal. So for the output, notice that it would be all the nodes values in the binary search tree, but in a level order fashion. So if you're given a binary search tree like this, notice that 3 gets printed first, followed by both of its children on 2 and 5, and then we proceed to print the children of 2, followed by the children of 5, 4, and 7. It's a level order traversal printing. And every single number is separated by a white space. So for the input, we have a number representing the number of nodes that we will read in, and each of these 6 lines that follow afterwards is the data for every single node to be inserted into the binary search tree. Fortunately for us, HackerRank is really nice to implement the insert function as well as the node, which is the building block of a binary search tree, and the logic to insert each value from the input into the binary search tree is performed for us. One salient point on line 29 is level order, in this case, would print out the value. And in this case, notice that the output of level order is not assigned to a variable. That's because the type signature of level order over here is really none. And in this case, the root would be an optional of a node. So from typing, import optional. So this function is responsible for doing level order traversal, and we will print out the contents of the binary search tree in a level order fashion. So with that, let's get started. So to perform level order traversal, what we can do is we can perform a breadth first search using a queue. And the idea is really simple. We will start off from the root, and we will take the root as our starting point. After we print out the contents of the root, we would add both of its children to the queue. And once we are done, we can assign the current pointer to be the next in line from the queue. And because we are inserting values from the binary search tree where the children gets added first, we are adding the children from the binary search tree in a layer by layer fashion. So similarly, because queues are first in, first out, if we insert the nodes in a level order fashion, then we would traverse the binary search tree in a level order fashion as well. So with that, let's get started with the implementation. The first check would be a simple guard, whether if root is empty. So if root is empty, we can return, because this means that the binary search tree we are given is empty. There is no nodes to print. So we will just return. So the next thing that we will define is a current pointer. This current pointer would keep track of the nodes in a level order fashion. So we will assign this to the root first. The next thing that we will have is a breadth first queue. This queue would allow us to traverse this binary search tree in a level order fashion. We will also be using the double-ended queue data structure from collections import double-ended queue. And this double-ended queue, just to refresh you, is a doubly linked list, and it is perfect for us to use as a queue. So the condition is as follows. So we are given a current node. While the current node exists, we will print out the contents of this current node. For in this case, because we want each value to be separated by a whitespace, we can override the print function. Notice that the print has an n parameter that is set to a new line character by default. But because we do not want a new line character after every value, we can override this with empty whitespace here. So once we are done, we can check whether if this current node has a left or a right children. So if that is the case, we will add it into the breadth first queue, so we can use it next in line in the queue. So if current.left exists, then we would just append it to the right of this double-ended queue. So current.left. If current.right exists, then we will do breadth first queue dot append current.right as well. And once we are done, we will set the current pointer to breadth first queue dot pop left. We are popping the value on the left of the queue. So this has the effect of having a first in first out behavior if the length of the breadth first queue is more than 0, else none. So this is so that we do not call pop left unsafely on the queue if it is already empty. And this is pretty much the implementation of our breadth first search. So let's run this. Let's pass the test cases and let's submit this code. So with that, this is pretty much how you can implement a simple breadth first search using a simple queue as well as a while loop. There's one additional bonus that is worth your time, which is that if you look closely at the output, we have an empty white space at the back of the standard output, but the expected output does not have a white space at the back. And that's because HackerRank is really lenient. They are not penalizing us for having an additional white space at the back of our output. But if we really want to remove that final white space, what we can do is check whether if this current pointer exists, only then do we print out the final n over here. So in this case, we will set n to be equals to an empty character, and we will just run this code again. And this time, notice that our output does not have that final white space as expected. So let's submit this again. And this passes all of our test cases. So I hope this demonstration was helpful to you. If you find this useful, please give us a like and subscribe, and we will see you in the next video.